Hello, F Sharp. How are you doing? So, today's video is a continuation of a previous one that I had done where I talked about using a bit array instead of a hash set for tracking assignments. Now, what this is an enhancement of that. And one of the things is that assignment is now composed of three different things. Instead of just the job and the machine, an assignment is a job ID, a machine ID, and an operation ID. And in this case, the number of possible jobs is still about 1,000. The number of machines is about 10, and the number of operations is also about 10. Now, why am I doing this video? Well, the problem with bit array is that it's nice in that you're able to say like, hey, set the value of a particular item in that bit array. But if you want to iterate through the values that are set in there, you can't do it. You'd end up having to like check every single bit. And that's horrendously inefficient, especially if a lot of the bits aren't actually set. So what I wanted to do is say like, okay, I'm going to take that same idea, except now I'm actually going to be manually kind of managing my own bit array. And the way I'm going to do that is I'm going to use an array of unsigned int64s. And so I'm going to use the same trick of mapping a job ID, a machine ID, and an operation ID to an index into an array of bits. But I'm also going to use an algorithm for quickly going through those. And then when I have a value that's set, I'm going to compute something from that. And I'm going to compare that to just using a hash set, which I used previously. So I'm going to go through some of this pretty quickly because it is just kind of a continuation of what I'd done previously. And I'm going to emphasize the new bits. What's also really exciting is that I put this out and say like, hey, look, this is faster. And it was not intended, it was not a troll, but it was a sincere statement saying like, hey, I think this is really fast. And if anyone can do something faster, I would love to see it. And what was really exciting is that I think within 30 minutes, an hour, a community member came back and said like, hey, here's what you could do. The community member's name was Maten, I believe. It's Swedish. And I am terrible at pronouncing non-English names, so I apologize for that. But it was really fantastic feedback. I'm not covering that part in this video because there's enough interesting stuff going on in there that I wanted to spend an entire video just on the optimizations that Maten proposed. And I think that it's worth that amount of time. So there'll be another video, which is a continuation of this one, but you'll see some of the code interspersed in here. So let's go in the two different approaches. One, which is a hash set approach, and another, which is a kind of manually rolled bit array. It is not the .NET bit array. It is our own custom one that we're managing all of it. So for my domain, I have, like I said, job ID, machine ID, and operation ID. And I'm using units of measure to annotate primitives because the CLR loves primitives. And I have an assignment, and that's defined as the product of the job ID, the machine ID, and the operation ID. And when I want to track that in a hash set, what I do is I take those three different indices, and then I just use bit shifting to map those values into an int64. So when I want to create an assignment in this case is just an int64 with the unit of assignment. I take the job ID, I turn it into an int64, and I shift all the bits to the left 32. So now the top 32 bits represent the job ID. And then the machine ID is bits 32 through 16. And the operation ID is bits 15 through 0. And so altogether, that makes an int64 that represents that unique assignment. And then I have another function here for decomposing those values back out. So if I have an int64, which is an assignment, this function just takes those pieces and breaks the pieces back out for you. And I use this as what I put in a hash set for tracking. Is this assignment available or not? And the reason I'm doing all this is that when I profile the algorithm, 85% of the time, the algorithm is spending on adding to the hash set, removing from the hash set, and then iterating through it. And this piece of code is running millions of times. So it warrants these additional optimizations. Normally I would not do this. But if you're someone like me and you're like, okay, well, how fast could I really make it go? Just because it's fun. It's fun to like just see how nuts can we be. So my bit version of tracking this is I'm taking a job count. When you create an instance of this, you give me the job count, the machine count, and the operation count that you possibly want to be able to track. I then compute the number of unsigned int64s we are going to need to track that, and I create an array containing that amount. And this is kind of my bit array that what it is. I'm treating it as a bit array, but it is not the .NET bit array. So I want to keep that clear. I then have some of the internal members that I need for being able to compute things. And when I want to add an assignment, you give me the job ID, the machine ID, the operation ID. It checks the bounds to make sure that you're not trying to add something that is outside of the domain that you said was going to be possible. And then what it does is it computes like, okay, where am I going to put this thing? So it's just calculating which bit location in the array do I need to set to 1. And then it says, okay, it's going to be in this bucket by taking that location, dividing it by 64. And then it gets the offset within that bucket by taking the location and subtracting the number of buckets times 64. And then this bit operation is just setting that value to 1. And then remove is very similar to it. Same type of thing. I'm all the same checks, computing the location, and then it is setting the value to 0 by saying, take what was in the bucket, and then you're going to AND it with an int64 where the location of interest is set to 0 and all the other bits are 1s. And when you do that AND, the location of interest is going to now be 0 and all the ones that were previously in there are still 1s. And there's a really fantastic video by I think the YouTube channel is called Creel. It's an Australian developer. I think he might be a professor. I'll have to double check, but he has some amazing videos on x86 assembly and bit hacks, and that's where I got all this, and it was extremely helpful. Now, here's the part that the .NET bit array does not support, and that is I need to go through all the set bits, and where it's set to 1, I need to compute something. And so I define a method that I'm calling map. I know it's not a true map in the functional sense, but it's the closest name that I could come up with. And what it is you give this collection a lambda, which takes the job ID, the machine ID, and the operation ID, and returns a result of some type. And here I create a stack where I'm going to be storing the results. And then I have a while loop where I'm going to go through all the different buckets in this backing array. I get the bit set out. Oh yeah, and let me note, like I did not come up with this algorithm. Oh dear, no. No. I searched for this algorithm on Lemier's, I believe, Lemire. Oh man. Blog. It's fantastic. The link is here, and I'll also include it down in the description for you to go to, where it has a great explanation of how this is working. But basically what it's doing is it's going to each bucket. It checks if the bits in that unsigned int64 are they equal to 0 or not. If it's not equal to 0, it means at least one of the bits is set. It then uses an instruction called the CTLZ. Oh man, I'd have to double check. My apologies. But basically it's saying like how many trailing zeros are in this bit set that you gave me. And so what that's doing is it's saying, hey, what's the location of the first one is what it's telling you. And then from there, I compute what location does that correspond to in the entire array. And then I decompose that down into the job ID, the machine ID, and the operation ID. I call the Lambda that you provided me with those arguments, and I push that result into the stack. It then clears that bit that we just computed for, and then checks, hey, are there any ones still set in this bit set? And then once all the ones have been computed in that bucket, it then moves to the next bucket and then checks there. And then once it's done, it's going to return that result as an array. Now, in this area is what I'm going to cover in the next video, and this is what was provided by Maten, I believe. Again, I believe that's how you pronounce it. And there's enough interesting stuff in there that I want to give it its own video. But that's what this approach is. And here in the tests, all you're seeing is, hey, creating a random number. I have the job ID bounds, the machine ID bounds. In this case, okay, I said 100 different operations for this. And so this is kind of like the way far bounds of what I would need to model in the algorithm that I have. I compute some values. So these are going to be the initial values that are already set in the hash set and in our bit set tracker. I then compute some values that I want to remove from it in our remove tests. I then have I compute some values like, hey, these are the assignments that I'm going to be adding to our hash set into our bit set tracker. I then create the hash set. I create the bit set, and this is the one. This one here, the inlining one, is the one that Maten did. I will cover that in the next video. And then I just have tests for like saying like, hey, hash set add, remove, and map. So adding elements to the hash set, removing elements from the hash set, and then mapping over the values, the assignments that are actually in the hash set. And then they do the same thing for the bit set tracker, bit set add, bit set remove, bit set map. And when I run these, we see that hash set add and remove are around 120 nanoseconds. And bit set add and bit set remove, this is our custom bit set tracker, is almost half of that, dramatically faster. And then for the hash set map, that's around 80 nanoseconds. And for the bit set map, it's 30 nanoseconds. So these are huge speed ups and really accelerate the algorithm and makes my boss very happy because performance is a feature in everything that we do. And so part of the reason people will come to us is because our stuff just runs faster than everyone else's. So, and what was fascinating is I put out a tweet saying like, hey, I think this is pretty wicked fast. If anyone can come up with something faster, I would love to see it. And again, the community comes back and says like, hey, not only can we do better, like this is dramatically better. And for me, that's just phenomenal. So in the next video, I'm going to go into that. But hopefully this was kind of like an interesting intro to how, we can take advantage of some domain knowledge, and instead of using a generic collection like hash set, we can say like, hey, we can do better. And one of the key takeaways I want you to have is that the reason this optimization makes sense is that for this algorithm, we know that we will almost always have at least one assignment per job. And so the number of assignments that you're needing to tracking is pretty high. And so that's going to be a pretty dense set of assignments. You're going to have a lot of values in there. So it's not sparse. And the reason that's important is because if you're using hash set, you're going to be tracking a lot of items in there, and the overhead associated with a hash set, like there are additional things hash set has to track in terms of the keys and buckets inside of it. And so there's just more overhead associated with tracking a dense set of values than if you just use bits. And the other reason we can do this is because for our simulation, we are mapping all the possible values down to this dense set of values. Like I know the operation IDs are going to be between 0 and 999. I know machine IDs are going to be between 0 and 10. I know operations are going to be between 0 and 100. And because of that additional domain context, optimizations like this start to make sense. If you don't have that additional domain context, I wouldn't do this because it wouldn't make sense. So something to consider before you try something like this, and this is definitely what I would put in the more advanced category of things. So we're exploiting our domain knowledge in order to get these additional speed ups. So hopefully that was a little interesting. Just things that you can do to potentially speed some stuff up in F#. If you have any questions, please feel free to comment or hit me up on Twitter. And I'm really looking forward to the next video where I'm going to be able to give some really give the additional optimizations their due time, because they're really fascinating, and I want to show you why they're faster. So hope to see you again in a few days. Have a good day.